You were the one who asked to partner with I did ask him to wait around after class. If he shows up, he will wait.
Okay, so all the way around.
Yeah,
Yeah.
I can do that than you asked. Yeah. Okay, let's start. Right. So we've been looking at optimization, and we had this general form of optimization, and we said that you can phrase many problems as optimization. Right? And last time we had this observation that any formulation in which you phrase as discrete optimization usually turns out to be NP-hard. Okay, so any optimization is like discrete optimization. By this we mean domain was a discrete set is usually NP-hard, even if the constraints are pretty natural linear constraints. Right? So this is something we said last time, and said that there are a few forms of optimization that we know are easy, okay, that we can actually do efficiently. And one of them is you want to do continuous optimization, have linear constraints and a linear objective. So this is what we call linear programming. So this can be solved efficiently. Okay. And there's another class which is called Convex Optimization, which is a superset of this and can also be solved efficiently but with some caveats. Okay, so linear programming can definitely be solved in Convex Optimization, and Convex Optimization can usually be solved on the So there's some caveats about how big the feasible set is and how much your gradients are and so on. Okay, so for all practical purposes, this is efficient. Okay. And so the main challenge in trying to use these methods is how can you express your problem of interest, your favorite problem, as some optimization that you can actually do efficiently. Okay. So that's the general focus. So today, what I'll do is I want to talk a little bit more about linear programming because I want to give you guys a sense of what is actually involved in solving a linear program. Okay. So today's class will be a bit more linear algebra heavy than previous time. Okay. So just a warning. Okay. All right. So let's start. Okay. So last time we saw. It's a very basic fact about linear programs, right? We said that every constraint can be expressed, if you think about it, this is like a half space.
Okay, so we had some basic observations about the geometry of these, like every constraint, linear constraint, is a half space. Okay, by this we just mean you have constraint like x1 plus x2 plus x3 plus 2x4 equals bigger than or equal to 1, let's say, and this would be a half space in 4-dimensional space. Right? So, and so this is so there is a plane that will be defined by x1 plus x2 plus x3 plus 2x4 equals x1. That would be a plane. That would be a it's called a hyperplane. Okay. So so suppose you have a constraint like a11 x1, a12 x2, plus a1 xn is bigger than equal to b1. This is one of the constraints, if you remember. And if you remember, we also wrote this down in shorthand as a1 transpose x bigger than b1. Okay. So maybe I will recap that also. So we let's add a page, right? So we said that linear programming we said that it's like you can think of this as minimizing c1, x1. So your variables are x1, x2 up to xn, and these are all real numbers. So this is a continuous optimization. These are all real numbers. And you want to maximize min of c1, x1 plus c2, x2, cn, xn. Okay, subject to A11. I will use capital and small letters kind of interchangeably, but maybe for consistency, I will use all small letters so that you guys don't get confused. But if I ever use a capital letter by accident, it means the same as the small letter. Okay. So A11 x1, A12 x2, A1n xn bigger than. And this constraint, we said we would write it in short form as A1 transpose x bigger than equal to B1. Where A1 transpose is just this vector that has A11, A12 up to so on. And this guy we would write it as C transpose. And similarly, you have A2 transpose x bigger than equal to B2. You have AM transpose x bigger than equal to B1. So, right. So each of these constraints, if you think about n-dimensional real space, so you have this is, let's say, n equals 3. You have 3-dimensional real space. Each of these constraints is a plane. So probably bad at drawing planes. And this is called a hyperplane. Okay, so it's an infinite plane. And like one of these equalities corresponds to a plane. Inequality just means all points on one of the sides. So that's a half space. So basic. Okay, so this is A1 transpose x equals B1 is a hyperplane.
These are also, in some sense, these are definitions.
So this is a hyperplane. And A1 transpose x bigger than equal to B1 is half space.
So each constraint is a half space, and it defines set of all x that are feasible. Okay, and now, if an x is feasible overall, it means that it lies in each of these half spaces. Okay? So the set of feasible constraints is what is called an intersection of half spaces. So in 2D we drew some examples of this. Like one half space was it was turning out to be this. All points on one side of a line. Another half space was maybe all points on this side of the line, of this line, of the second line. Another half space was maybe everybody on this side of this. So then the feasible set would be this line. So the feasible set is just set of all points that satisfy each of these half space constraints. Okay. So this is the formal setup. So any questions on this? Okay, so this is so this is just basic geometry that you should be aware of if you're thinking about linear programs. Okay, so that's why I'm spending time on this. Right, so if you have questions or notational questions, is what I would expect to just ask. All right. So this is the notation we will use. And so a couple of observations we had last time. Okay. So the first thing was, so how do you visualize these linear constraints? One of the useful facts was this. Okay. So we said that if you have a linear function, in this case x plus 2y, okay, and your variables are x and y now, then then the level sets of this, which basically means x plus 2y equals 1, x plus 2y equals 1.5, and so on. So these would be parallel lines. Okay? And in general, they would be parallel hyperplanes. Okay? Like in high dimensions, this would just be planes that are parallel, and the orthogonal direction would correspond to these set of weights. Okay? So in this case, the direction of this vector where things increase. Okay. So this would exactly correspond to the coefficients. In this case, the coefficients are 1 and 2. Right? So this would be the direction 1, 2. Okay. And you've got to scale it up and so forth. But that's fine. Okay. Scale it so that scaling doesn't change things. Okay. So this is another very simple geometric property. Okay. So any questions on this? And intuitively, it makes sense, right? Like if you take any point here and add 1, 2 to it, okay, then this value of so if you took any point out here, let's call it x0, y0, and you added 1, 2, so you had x0 plus 1, y0 plus 2. Then if you compute this function x plus 2y for that new point, it would be the old function value. Okay, so it would be f of let me write it as c transpose x0 y0. So this is just defined to be x0 plus 2y. So if you now look at c transpose and x0 plus 1, y0 plus 2. This would be whatever this old thing is plus some phi. Okay, so in this case, it just happens to be the length squared of this vector that we are choosing. Okay, but in general, so in this case, there are no negative values. But even if these directions had some negative things in it, it would always be a positive quantity. Okay, so that's what I mean by if you move along this direction, your value will always increase. Okay, and that's the property. And using this observation, we said that now you have a great way of solving a linear problem, okay, or at least characterizing a solution. You know that the objective function is just defined by how far along you are in this direction, right? So there is a specific direction corresponding to the C. So one of the observations is, okay, so this is jumping one step ahead, but maybe I'll do this, is that one of the observations, this is again of last time, is that maximizing, I think we spoke about minimizing last time, but they're both the same, so let me just talk about
Yeah, okay, I did speak about minimization even this time. So let me just minimize. So minimizing C transpose X in a particular subject to some feasible region. Okay, so this is, for convenience, let's call our feasible region R.
Okay, so R is your feasible. So minimizing C transpose X in R
Is the same as finding the bottommost point. So you have this direction C along which
the objective value increases, right?
so now now you want to minimize it. So you want to find
the furthest point in the direction minus C. Okay,
so minimizing C transpose in R is the same as finding the furthest point in R in the direction of minus.
okay, and this is a clean geometric interpretation of what the optimum value should be. Okay, so if you have an object and you want to find the point in that object that minimizes a linear function, you just have to see how that linear function is defined, that C that defines the linear function, and you go in the opposite direction. Okay, you go as far as possible. Okay, so in this case, the direction of negative C would be this, and therefore you just take the furthest point in that, which in this case happens to be this one. Okay. And last time we also said that this characterization gives us a simple nice theorem, which is that there is always a vertex or a corner point of this polynomial That achieves this minimum value. Okay. Assuming that the minimum value is finite. Okay, so it could be that the polytop is unbounded, in which case you go off and there is no place where the minimum is achieved. Okay. Or if it's finite, there is always one corner point of the polytop at which this optimum value is achieved. And somebody asked a nice question last time, like, so what if your C was like this, but your feasible region looked like this? Your negative C was like this, and your feasible region was like this, so this was perpendicular. Right? So in this case, what we said is that either of these 2 points also achieve the minimum. And therefore we said that the theorem is not exactly saying that the corner point is only achieved at the minimum is only achieved at corner points, but it's just saying that there is some corner point at which the minimum is achieved. Okay, so this is how we fixed this degenerate case. So the theorem, as I stated, it needs to be modified slightly, but for the sake of intuition, I think this is still the nicer theorem. Okay, so the optimum is always achieved at a corner. So, alright. So this is the theorem that we saw. Okay. And the other thing we said is that the feasible region can sometimes be unbounded, in which case sometimes the optimum value could also be unbounded. Okay. And geometrically, we saw an example where you could have a feasible region that's defined by half spaces that look like this. This is simply unbounded, right? So on that side there is no corner. So you can have this kind of situation. In which case, if your minus C was along something like this, you would not have any. I mean, you can decrease the objective arbitrarily. Okay. So this is these are some of the things we saw. And some of you were a little confused about this, but what I said last time in proving this theorem, this hand-wavy proof that I gave of keep going down until you hit a face, and then keep moving along this line until you move around. So that's just an approach to proving that theorem. It's not exactly an algorithm, okay? Because if you try to go ahead and implement this, right, like it's a very intuitive description, right? Like how do you say you move along this direction? You start at some feasible point. Then the question becomes, how do you start with a feasible point? How do you find a feasible point to start with? In fact, it turns out that finding a feasible point is as difficult as solving the original problem.
Okay, so this is, I mean, because you can always write the objective as one of the constraints. Okay, so you will see this in your homework, but you can. So finding a feasible point is as difficult as finding the optimum solution, because you can always write an objective as a constraint, and you can move that thing around. And yeah. So anyway, for those who've seen it, this is straightforward. Otherwise, you will still see your homework. So. Feasibility. Okay, so in particular, what I want to emphasize is that what I described last time was not an algorithm for actually finding out. Okay, the only algorithm that comes up from this theorem directly is the following brute force one, which is find all the possible coordinates, okay, and check which one gives the optimum value for the weight. Because we know that that there is one. I mean, there is a coordinate that achieves the minimum value. So one possible naive approach could be find all the coordinates. Okay. Check. Check which one achieves the smallest value. Okay, but there's something you've got to be careful about, which is that not all corners are feasible. Okay. Can someone think of why? Actually, how would you find a corner? Okay, like suppose I gave you a bunch of equations. Okay. So let's start with this more basic question, finding a corner. So can you characterize every corner point if I give you the equation A1 transpose X was equal to B1? And I told you that you were in d-dimensional space, right? No, I guess we assumed n-dimensional space. Okay, so you have n variables, so everybody is in n-dimensional space, and I gave you a bunch of m inequalities. How would you find a corner point of the region defined by these m inequalities? So I think you should think of the case n equals 2, right? In 2 dimensions, how would you find? Yeah?
Take n of the constraints and find where the limits intersect.
Yeah, so this is exactly what you would do for the case of n equals 2, right? In the case n equals 2, you have lines in the plane that define these constraints, and your half spaces are basically one side of these lines. Right? So to find the corners, you just have to see where these lines intersect. And in the case of a plane, you would take every 2 lines and you would see where they would intersect. And that would give one of the points of intersection. Okay. So, and in a high dimension space, it's exactly like you were saying, this would be the natural generalization. Okay, so you take n of these, because you have a system of m equations in, if you have n variables, then you need exactly n linearly independent equations to get one point. Otherwise, you would get multiple solutions, no solution. Okay, so yeah, so finding a corner is basically choose n of the n equations, okay, and solve for the solve for the common point on these hyperplanes. Okay, so this is how you would find a corner point. Now, my question is: think of the case again in 2 dimensions. Can you come up with an example where not every pair of equations gives a feasible point? Like, could it be that you do this and then you find a point, but this point is not feasible?
Parallel lines.
Sure, parallel lines is one. What about, okay, assume they're not parallel. Can you? Yeah.
I mean, you have an intersection between 2 hyperplanes that's outside of your R region.
Exactly. So what he's saying is, let's say you have a region that is in a plane that is defined by something like this, Okay. Now, if I happen to choose, let's say, this plane and this plane, so these are two of the lines, but their intersection happens to be at a point that is outside. Okay. Now, I should not be considering this guy as a candidate minimum, right? Because this is outside the feasible region. Okay. So when you're trying to solve for, when you're trying to come up with an algorithm, you should make sure that the point you found is also feasible. So this is what I meant. So one simple algorithm would be find all possible corners, find all potential corners. Okay, check feasibility. Okay, and then find the minimum value. Okay, of sequence. Okay, so this would be a valid algorithm. Okay, so you find all possible corners by choosing n equations of that. Yeah, and then check for feasibility, and then you find the minimum of these guys of this linear. Okay. All right. Yeah.
The full stop is that so that's the definition is you put every possible corner on the polytop or
No. So it is only things that satisfy all these constraints, right? Like in this example, this like the corner here is not included in the polytop, right? Because only this inside region. So this is called the polytop. Okay, so this feasible region R is another name for it is the polytop. Yeah. So yeah, formally defined it. A polytop is just the feasible region. It's called a polytop because it's defined by these planes. Yeah. Okay, so that's just the definition of. Some people call it polyhedron. They're all, but there's some mild finiteness thing. If people say polyhedron, it usually means it's also finite. Or maybe it's the other way around. I always forget. but yeah, one of them is always finite. One of them is not. One of them need not. So, all right. So. Okay, so this is that. Now, so this is an algorithm, but if you think about it, so we have m of these constraints, and we are picking all possible n of them to find these corner points. So this algorithm is pretty inefficient. It takes time. That is m choose n. And if you think of like m as being 10n or something, this would be exponential. Okay, this would be exponential. Now, there's a better algorithm that was proposed by Danzig. This is one of the earliest interesting algorithms as well. Okay, so this is called the Simplex Algorithm. And what he showed is a clean way of moving from one corner point to a neighboring corner point. Okay? And one of my goals of today is to just describe this algorithm and see how it works, and show you guys how it works. Okay, so this will give you a sense of how to reason about linear programming. I mean, how to think about this space, and yeah, it's also, I feel, something that people use all the time in practice to solve linear programs. Like most of the packages you will find will use some variant of simplex, and yeah, so there are also other methods called interior programming methods. So I'll just do a summary of it in the end of other methods. But simplex algorithm is one of the things that people really use a lot in practice. Okay. So we'll do basically see how this algorithm works. Okay. And the main idea is, again, you want to check all the corners, but you don't want to check all the corners. And what you do is you start with one corner. And as I was saying, in some problems this could be difficult in itself. Okay, but you hope for the best, and it assumes that you start with one of the corners, and you keep moving to a neighboring corner. Okay? So let's see how that works. And so let me describe the high level of So start with one corner point which we call V. Okay, so this is often called the basic feasible solution.
Okay, so if you see this literature, they always talk about this thing called basic feasible solution. Okay, so that's how you start off,
And you always move to a neighbor
We'll see what I mean by this in a little bit.
you always move to a neighbor that has a lower objective value.
Okay, and if there is no such neighbor, then you stop and return your solution. Okay, so is this accurate? Yeah. So you can think of it as doing local search on just the neighbors. And understand what it means to be. This is doing local search on the set of corner points.
So this is local search.
So as a side note, one might, so this just for those of you who are interested, is note that I said that this brute force algorithm essentially tries to check all corners and it takes time, something like m choose n. Like you might ask, are there actually m choose n feasible corners? So it turns out the answer is no. Okay, so it turns out that
In general, there are only something like m choose n by 2 feasible corners.
So this is an interesting fact. Okay, so it's not really a fact. There are only m choose n by 2 different corners. Okay. In particular, in the plane, if you have n hyperplanes, their points of intersection could be n choose 2 different points, but the feasible region could have only n things. And intuitively, this is obvious in the plane because it's like it's a polygon with each of those n planes could figure once. They can't figure it twice. Okay. So this is a more general. Okay, so the runtime of the brute force, you can improve it slightly. Anyway, so this is just an aside. Okay, so the simplex algorithm,
Start with the first basic solution.
Yeah, so this we don't know, right? So the simplex algorithm relies a lot on assuming that you can find one. So that, as I was saying, so simplex algorithm typically is, in the worst case, this is exponential time. It could even take exponential time to converge. Okay, so there are examples in which you can prove that you take something like exponential time to converge. But in practice, often finding one feasible solution is not a problem, and it also converges pretty fast. And there are various heuristics people use because you have many neighbors that have a lower C transpose X value, and you've got to pick whom to move to and so on. So there are a lot of heuristics people use to decide which one to move to, and that often affects the running time a lot. But these are all heuristic. So in fact, there's a heuristic called random neighbor that turns out to work much better. Okay, so you move to based on how much, some probability distribution based on how much the value drops. Okay, so that turns out to work the best. So it's called random neighbor. Okay, so we are getting a little bit ahead of ourselves. So what do we mean by a neighbor? Okay, so that's the first question that I want to ask. Okay, is there a clean geometric way of characterizing what a neighbor of a point is? You guys, like think again 2D, right?
these things, you've got to think 2 or 3 deep and hope for the best when you extend that intuition, right? So if I told you this is one neighbor, that's the intersection of, let's say these lines are L1, L2, L3, L4, and so on. And suppose I told you this point is where I started with you, okay? And I ask you to find what is the neighboring point, right? So intuitively it's these two, but how would you try to characterize this? Yeah.
If you remove from your solution one of the dimensions and provide another line.
Yeah. So intuitively this is what you would do, right? Like if I had to move to this point, so then I would observe that this one was L2 intersect L1. This guy is L2 intersect L3. So the L2 is common, right? So I'm in some sense removing L1 and I'm trying to add L3, and that would give me the next one. Okay? And I could have kept L2, tried L4 as well, that would give me this point. This point is not feasible. Okay, because this point does not satisfy the equation for L3. But in general, you could imagine doing this thing, right? So in general, a neighbor is of the neighbor of B is a point that has precisely n minus 1 equations. In common with B. Okay. So this is again this is let's call this B prime or something. Point B prime. So B prime is the intersection of n other equations. Okay, but the two sets of equations have n minus 1 things in common. So if you assume that B was let's assume for simplicity that this is like A1 A1 transpose X less than A1, AN transpose X less than then B prime would be one of these equations would be defined by one of these equations replaced with one of the other. B prime is one of equals B prime replaced by okay. So this gives us a characterization of how to find V's, right? How to find these V primes. Like you were saying, remove one of these equations, put a new equation in, okay, and now you get a different point. Check if that point satisfies all the constraints. If it does, then this is one of the neighboring vertices. Okay, so this will be. So this observation implies a way to find. Okay. Once you have this, now the description of the algorithm is complete. Right? Because you know how to find neighbors, and note that this is a very clean local search algorithm. Every point is defined by n equations. Each time throw one equation out, add another equation in, check for feasibility, and check if going there improves it. So this is a very clean local search algorithm. Alright, and then comes the next point. Okay, so the next thing is the correctness of this algorithm. Right? So we stop if there is no neighbor such that the cost improves.
And the question is, why should this be a valid? So can you not get stuck, right? Like, could it be that in some sense you have an optimal solution? I mean, you have some V here, which at which point you are currently, and maybe the true optimum is this V star. But these neighboring points were kind of these neighbors were not very useful. Okay, like the neighbors had a larger cost or something. Sorry, yeah, the neighbors had larger cost than V, which is why you concluded that V was a local minimum. Okay, and but V star had a lower cost. So in principle, this kind of thing could happen, right? So we've got to rule that out. Okay, so we need to show does no neighbor with a better cost imply that this is actually the global form. And this is often the thing with local search, right? If you remember, like even for this like swaps example we did, it was a non-trivial proof to show that if you get stuck, you're actually optimal. Or in that case, you are close to optimal. In this case, you'll actually be optimal. So this is what we would like to show. And one thing I'd like to emphasize, this is a slightly, don't worry if you don't understand this problem, is that this does not follow from general results about convex optimization. So one thing we saw a few lectures ago when we were doing convex optimization was that in typical convex optimization, a local optimum is also a global optimum. Okay? So that would be true if I was actually checking every direction around this V and trying to move along that and seeing if I'm improving the cost. Okay? I'm not doing that in this algorithm. I'm only checking this point and this point. And the fact that these two guys were larger were worse basically I'm concluding that V is much optimal. So it's not like typical convex optimization local search where you actually check every single point in your neighborhood. Okay. So this is, as I was saying, this is an integrate point. This is not the same as local op equals global op in the context of convex optimization. That's the reason this requires a slightly different proof. Okay, it actually requires a proof involving the structure of the linear program itself. But this is something that it's nice if you understand this. Okay, so maybe I'll pause for a.
Is it not useful to say that the optimization function is monotonic since it's first?
Yeah. So it is monotonic, sure.
Anytime anywhere close to the optimum, you have to
Right. But see, you're not taking every. So in this picture, right? Like I have this V star, which is probably the true optimum. But I have V, and I'm trying to argue that. So in some sense, you have to argue that if V star is a better point than V, then one of these 2 points, one of these guys, is also a better point. Okay? And what regular convex optimization will tell you is that if V star was a better point, then some point close enough over here. This is, let me draw it with a different color. This point is better than V. And this will follow just by some linearity. Okay? Because if you reduce cost by going all the way to V star, you also reduce by going half the way here, and so forth, and smaller. Okay? So this will follow from convex optimization. But I'm not allowing you to move to that point which is close to V. Right? So I'm only allowing you to go to either that point or so that's why this requires proof. In this
setting, it so happens that any point like this green point can be written as a convex combination of this point and this point. That's the reason you can still show that one of those two will still be valid. So that will be what I will show. But this is something you should understand. Okay, so that doesn't follow immediately from convex optimization. So yeah, as I said, this is slightly advanced thing, so it's okay if you don't understand. Yeah. No, no. So this will actually be the global optimum. It's just that I'm saying that it requires a more intricate proof. You can't just appeal to canonical convex optimization arguments. So we will prove that this actually will always produce the global optimum. Yeah. So yeah, that's the point. Okay, that good question. In case people got confused, I'm not saying that local optimum is not the global optimum. It's just that doing that requires a bit more effort than just saying, hey, local optimum equals global optimum for all convex optimization. It doesn't follow from the generic all convex optimization. Okay. Yeah. All right. So okay. So let's understand this a bit more. And so let's formalize what we wrote last time. So this is, as I was saying, it's a little bit linear algebra heavy, but it's nothing very deep. Okay, but it requires you to parse some equations. So let's start with this point V, like we said. Okay, and suppose V was the intersection of A1 transpose X equals V1, A2 transpose X equals V2, AN transpose X equals V3. Okay. And let us denote by, so you have n directions out of V, okay, which are probably the directions in which there are neighbors. Note that it doesn't really matter how far these neighbors were, neighboring vertices, because if your cost increased from V to a point out here, it will also increase from V to a point out here, because this is a linear function, right? So if your cost increased or decreased along this line, it's only the direction that matters. Okay? So the exact magnitude of the movement doesn't matter. Okay? So this is one thing that we define. So let's only care about the directions. Okay? Let's not care too much about the magnitude. And as I was saying, you get n different directions, n different neighbors. So we get n different neighbors of V, each obtained by dropping, like if I call this direction, let's for simplicity call this V superscript I. Okay, so you have V1, V2 up to Vn. So each obtained by dropping each Vi, obtained by dropping the constraint AI transpose X equals Vn and replacing that. Okay. So actually, yeah. So why wouldn't you get? I mean, you can replace by any others, right? So why won't you get multiple neighbors like this?
Okay, so firstly is this, let's make sure you understand what I have defined, right? So each direction V superscript I, okay, is defined as the direction you get by removing this constraint AI transpose X, the ith constraint of these things, and replacing it by some other constraint, one of the other m minus n. I'm just saying that if I replace by one of the other ones and a different one of the others, doesn't really matter. They're different. And you see why. Yeah, again, always think 2D. That's the hint. It's like in 2D, you have only two constraints, A1, A2. So if I replace A2 with a different constraint, let's say I had four others, right? Like A3, A4, A5. If I replace A2 with A3 and if I replace A2 with A4, what would the difference be? So let's go back to this slide. We can draw this. Right? We have this guy, this V guy that we will draw being like this. And this I am saying is this A1. Sorry, this plane is A2 transpose A2. And V1, I'm defining it as something that is lying on that line, but not on this. So this direction is V1. Because I'm dropping A1. And this direction is. So now I'm asking you, if I drop, let's say A1x equals B1, I replace it with, then that means that I'm on this line, because I'm keeping A2x equals B2. Now let's say I want to intersect it with A3 transpose x equals B3 versus A4 transpose x equals B4. How will these 2 points look like? So the intersection of this line with one. Yeah. Yeah.
Only one of this intersection will be uniform.
Yeah, so both of these are of course points on this line, because I said they still satisfy the equation for 2, right? So they are on this line, one of them will be here, one of them will be here. And only one of them, so the lines will probably look like this versus something like this. The point is that only this guy can be feasible. Okay, only this one can be feasible. This one cannot be because this is one of the hyperplanes. So this is the reason you can just say that every point has exactly n neighbors. Okay. So this is one of the nice properties you can come up with, right? Like if you're in n dimensions, every point has exactly n. In 2 dimensions, this is obvious. If you have a polygon, every vertex will have 2 vertices neighboring to it. And the formal proof of this is something like this. Okay, like you go in one direction and you can have only one of its things. Okay, so alright, so this is simple fact, but it just you have to realize that it also needs proof. Okay, that so you have n of these directions that define these things. So and we've called them V1, V2 up to Vn. Alright, so what I want to come up with is a clean definition of what these directions are. Okay? Turns out that these directions, intuitively we know what they are. They are basically you keep all but one of them fixed and you move along the other direction. But is there a easier mathematical statement? So
for that, let me just write down this matrix. Okay, so this is an n by n matrix, and the ith column of this is V sub I. Okay, so this is the direction starting at this point V and okay. So let's call this matrix X. Now my question is, what is, so at this point I've just defined, right? Like I've defined the V's, I'm just constructing a matrix where the V's are the column vectors. And each one is a direction in n-dimensional space, so this is an n-dimensional vector, this is an n by n matrix. So now I would like to ask, so what is, so let's consider a matrix A. So A, which I define as, this is again A1 transpose here, A2 transpose here, so these are this is the constraint matrix in some sense. Okay, so this is just A1 transpose A2 transpose as the rows. And my observation is what happens to A times X? What can you say about A times X? So if I multiply, actually let's do this column by column, right? So if I have to multiply A times X, I have to multiply this row with this. That would be the first entry. Then I have to multiply this row with this column and so on. Right? So if I multiply, let's say, the first row of this with the first, let's say the second column of this, what would I get? So the first row is A1. Right. So yeah. So let's examine what we get. Right. So my question is, what is X? Right. So the AX, the I comma j entry of AX is basically AI transpose times B superscript j. This is by definition. This is the definition of matrix product, right? Like the ijth entry of the matrix product is ith row dot product with the jth column. Okay. So this is that. Now my point is, how was Vj chosen? So Vj was this direction that satisfied all equations except the jth one. Right? That was the definition of Vj. Okay, so yeah, so let me write this. Unfortunately, I can't show two slides at the same time. I would like to keep this, but not. Okay. You have a very small thumbnail. Yeah.
Is it a symmetric map?
No, neither of these is symmetric matrix. Yeah. So A is the constraint matrix that need not be symmetric, and these directions V could also be just any directions in the plane. Okay. So, but they are, as we will see, they will be invertible. Yeah.
It looks like you're evaluating each of the directions with each of these ones, so the
Yeah.
product should be like which directions are possible.
Right. So, but what does it mean that which directions are feasible?
It means it's a row in the file matrix where every value is true with regards to this.
Right. So yeah. So that's exactly what we will try to use. Okay. So let's let's try to examine this in a bit more detail. Okay, how could I write Vj? So Vj right now is intuitively some direction, right? But what it means is that it was some point x sub j on this line minus v. Right? V was the point that we started with. So v sub j, let me just write it as x superscript j minus v. Because v satisfied all these equations. Now I'm asking you what is AI transpose times Vj, with AI transpose times xj minus v. What is AI transpose v? Remember, we satisfied all these constraints. So what is this is what you were saying, right? What is AI transpose times v? Yeah, it's exactly bi, right? So it satisfies v satisfies all these equations. Therefore, AI transpose v is exactly bi. So this is something minus bi. Okay. And what is AI transpose xj if j was not equal to 1? Would it be bi or would it be something else? That's the question. Remember, I told you this point xj satisfies all the equations except the jth one. That's how this direction Vj was defined, right? The direction Vj was defined as the direction where the points satisfy all the equalities except the jth one. So if I was not j, then I claim that if I is not equal to j, then I claim that this is bi minus. Okay, just see. This is my claim. So I'll pause here for a little bit so that you all believe it. So, okay, because xj was defined as the point that satisfies a point along this direction where all constraints except the jth one were satisfied. So in particular, the ith one was satisfied if I was not equal to j. And so this is exactly what we have. And so what this means is that A times x is a diagonal matrix. Because A times x has no ijth entry whenever I is not equal to j. Okay. So this is what we have. Yeah, so it does also tell you how much the cost. I guess the c is not involved. So if you multiply this with the diagonal of c or something, then yes. Otherwise, no. So the c is not involved in the definition of this matrix. Right? Yeah. Okay. All right. So this is a diagonal matrix, and now the point is that I could always scale the direction of the above, so you can pick. I mean, you can think of ax as just the identity. So here I'm doing a little bit of hand waving here. Can think of ax being the identity, and the reason is very, very trivial. Okay, because suppose I took any column of x and I scaled it by any constant, like scale it up by 2. Okay, then all I'm saying is instead of moving in the direction vi, I'm moving in the direction 2vi, which is exactly the same direction as the direction vi. Okay? So scaling of x is not important. Okay? So scaling columns of x, and you can even scale the columns differently. Right? Like I can scale this column by 2, this column by 1.5. This would still be a set of valid directions along which we are defining. Okay? So think about this a little bit offline because we are slowly. But you can actually think of A times X as being identical. Okay? And this X gives you the set of all these directions B up to some scales. Okay? So what this means, oh sorry, yeah. So what this means is that X is basically A inverse. Alright, so X is basically A inverse. Okay? So if I gave you a point on a corner point of this polytope, and I ask you what are all the neighboring directions, okay? And the answer is you look at all the equations that define this corner point, let them be A. Okay, so let the matrix of those defining equations be A. You invert that matrix. The columns of the inverse are precisely the directions you move in order to get to the neighboring points. Okay. And this, I think, is a very clean characterization, right? Because now if you had to implement Simplex Algorithm, all you have to do is you have a vertex which is defined by a bunch of equations, and you just have to, and you look at those matrix defining these equations, take the inverse of that matrix, and the columns of that inverse give you exactly the directions that you have to move in. This is clean geometric fact. So, okay, so let's let me pause maybe for a minute if you have questions. But this fact is the reason I did all this, because it's a nice fact. Right? So the moral is that the directions we have are simply the columns of phrases. Yeah. Yeah. So because you solved A and got a point X, right? So that's the reason it's inverted. So you solved for A and got the point B, which means that they were inverted. Is that also your question?
So do you mean Vj is no longer the position of the neighbor? It can be
It's the direction.
The direction.
Yeah. So Vj is some scaled version of this. Okay, so it's not necessarily the neighbor, some scaled version. Yeah. So that's a great point. Okay. All right. So this is so this tells us, this gives us the means to argue about what we want to achieve. Okay. So we wanted to prove that local optimum is kind of the global optimum in this case, right? And at least now we know how to characterize the neighbors, and they have a clean characterization. Okay. So now let us see what happens if, let's take this picture that we had earlier. Let's say V is this, and this is V sub 1, this is V sub 2, maybe we have 3 dimensions of V sub 3, and let's suppose that the optimum is V star, which is somewhere here. Okay. V star is the optimum value, and the claim that we want to do is if C transpose V star is less than C transpose V, then there exists some J such that C transpose V, I have to be a bit more careful here, V plus Vj is also less than C transpose V. So remember, I am defining these as the directions. Okay? So if I want to point along this, it would be C transpose
v plus some constant times v1, v plus a constant v2.
So this is what I want to write. Or in other words, C transpose Vj is less than C.
Actually, when I went there, I realized that I write way too big. I'm sure you guys can see even if I don't have this size. But yeah, so any questions about this? Any questions about this? Okay. So what I said earlier is equivalent to this statement. Okay? Like if V1 is that direction, V2 is this direction. Moving from V along V1 is like saying you go from V to V plus V1. Moving along Vj means you move from V to V plus Vj. That's what this is. We are saying that moving to one of the neighbors reduces the cost. Okay. So that's what this is. Okay. So this is all right. Now, how would you go about proving a statement? What would be a sufficient condition? So this goes back to again, yeah. So this will help give us a nice way of characterizing a nice geometric fact also. So I will write the claim, and I will leave you guys to kind of parse it. What the claim is. So this let me not keep writing claims. Let me write this as a theorem. And to prove the theorem, we'll use this claim. So it is if so V star minus V. Okay, so this is the direction of V star. Can be written, can be expressed as sum over I alpha sum over j, alpha j v j, where alpha j are all bigger than. So this is the claim I want to make. In fact, not just for V star. So I would like to make it for any point, for any other feasible point in the polygon. Okay, so for any point in R, point X in R, the feasible region. The direction from V to X, okay, can be written as a non-negative combination of these lines that go out of. This is an interesting fact, right? Like in 2D, this is like saying that you have, you have these two things, and this is some V. So you have, then it's saying that any point X here, then this direction X minus V can be written as some positive combination of these two directions. Okay, like this, this plus something times. Intuitively, it's highly believable, right? Because if you, and that's like saying, it's this direction has an acute angle with this and this, which again is intuitively quite believable. Actually, it's not acute angle with both, but you can still write it as a non-negative combination because. This angle need not be acute, right? But the point is that you can write it as a positive combination of these. So this is what I want to claim. Okay, and this is again, as I was saying, this is another nice geometric fact you might want to know about polytones, right? Like you have these. Every corner point is defined by a bunch of equations, and these rays that define the neighbors are
basically columns of A inverse. This is what we established some time ago. And every other point in the polytope can be expressed as some positive combination of these rates. And this is a nice fact to know. And yeah, so the proof of this is actually relatively easy. So let's do that. But first, if we prove this, I claim that we are done in proving this here. Do you guys see that? This you guys should be able to see. So if I tell you that V star minus V is some positive combination of these guys, okay, then I claim that then this must be true. If you want this to be even more obvious, then this is equivalent to saying C transpose times V star minus V less than 0. So V star minus V satisfies C transpose times that, and it can actually be expressed as some positive combination of these guys. Then could it be that C transpose times Vj is always positive, but sum of alpha j times that is negative? Right, so it can't be. So this is an obvious proof by contradiction, right? Like you say that if suppose there is no such j, which means that for every j C transpose Vj is bigger than or equal to 0, then you take some non-negative combination, sum of alpha j times C transpose Vj, that is also positive, that is also non-negative, bigger than or equal to 0. And linear product, and the inner product is a linear thing, therefore C transpose times sum of alpha j Vj is also bigger than or equal to 0. And that basically contradicts the fact that C transpose times V star minus V is less than 0. Okay. So I don't know, maybe this was obvious only to me, but do you guys want me to write it out? Okay, so let me, yeah. So proof is by contradiction. Okay, so this part proof is by contradiction. Okay, so suppose there is no such J, and you just take linear combinations. So this is probably an interesting exercise for you. So, all right. So this is so this is how. Therefore, proving this claim is basically what we need. So, all right. So let's do this. So we are at this point 3. We have all these directions, V1, V2, V3, okay, and we are given this point X inside the polygon. And now I'm telling you that, yeah, let's look at X minus V. So that's this vector. Firstly, I want to claim that you can write it as some combination of these VI's. This equals sum over I alpha I VI, where alphas are not necessarily positive. So why is this? When can you write a vector as combination of other vectors? How would you? Yeah, so what he's saying is that V1, V2 up to Vn, they are actually linearly independent and there are n of them. So they are actually a full basis for all of Rn. Okay? So in fact, it's not just this x minus v, any vector in Rn can be written as a linear combination of these guys. So you can actually write it. So there's always some linear because Vi's form the all right. So this means they form one. They can write anything. now let's look at ax minus a.
Well, A was exactly this matrix that I defined earlier, right?
Like A had A1 transpose, A2 transpose, A.
Okay. So this was yeah. This was.
Let's not even do A. Let's just do a simple. Let's just do AJ transpose X, AJ transpose. So now this would just be sum over I, alpha I times AJ transpose.
So I'm just multiplying both sides by AJ. And I can linearize this. Okay, so this will.
Alright, so this one is equal to 0
Because B actually satisfies this constraint. And what is this guy? This is a feasible point. X is some feasible point. We know that every feasible point must satisfy all the equations.
So we know that AJ transpose X is bigger than or equal to BJ. Oh, sorry, this is not 0, this is BJ.
Okay, because it satisfies it with equality.
And this guy is bigger than or equal to BJ. In particular, the left hand side is bigger than or equal to BJ.
And now what is the right hand side? The right hand side is you can use the exact same argument to say that this is a sum over different i's. But we already saw that AJ transpose BI is 0 for anybody who is when I is not equal to J. Okay.
So this is exactly equal to alpha J times AJ transpose BJ. And by the way I picked BJ, this turns out to be equal to 1.
Because these were the columns of the inverse. Okay. So since we are out of time, let me just yeah.
So this is because BJ were chosen to be the columns of the. Okay. So this means that this is equal to 1, and this guy was non-negative, and this implies that alpha is.
So this is kind of a clean proof, but again, as I said, it involves a bit of linear algebra. But the fact is something which you should know, even if you don't understand the proof, even if you don't recall the proof. Just that any point inside, you can write it as some non-negative combination of these directions.
And this basically implies that
Local optimum is the same as global.
Alright, so
maybe I'll end by just mentioning this one thing. So this is called the Simplex Algorithm, and it was one of the early algorithms proposed by Danzig in 49. Okay, and it's known to be exponential time. For a long time, there was this very big open question, like can linear programming actually be solved in polynomial time? Okay. And there was this breakthrough by Katian, who was actually from the former Soviet Union. In fact, at the time, apparently the Soviet newspapers mentioned this as this is so the Soviet Union is winning the optimization race kind of thing. Right? So they pitched it as a big victory for Russian science. So it was that big a deal because people used linear programming everywhere. It turns out Katian's algorithm was actually much less practical than Danzig's algorithm. Okay, so in practice, this would still work much better, but that had theoretical guarantees.
So, but yeah, so this led to a lot of other algorithms called interior programming methods, interior point methods. And there was a classic algorithm by Kalmarkar in '84. And this was like the answer to the to Kachan's algorithm, right? So this had both theoretical guarantees and it worked pretty well in practice. Okay. This was patented by Bell Labs for a long time. Yeah, so that's a long story. But yeah, anyway, so this is what we saw is called the simplex algorithm, and it's nice because it tells you about the geometry of how these objects look like. Okay, these other algorithms are a bit more intricate, but they are both polynomial time. Okay, so simplex algorithm could be it. Okay, so let's stop there. Next time we'll see how to use these things.
Oh yeah, yeah. I will.